Poincaré map. We consider a robot described by some state equation with an input u, and for the input u we have a heading control given by u equals the sign of the desired heading psi bar and x3, which corresponds to the actual heading of the robot. x1, x2 correspond to the position. Once this heading control has been done, the robot has to obey the following automaton given here. As a first question, we have to show that we will converge to a stable limit cycle. And as an initial condition, we take this vector. Of course, another vector could have been taken. So this is my system, and the input of this system is u, which corresponds to a rotation rate. x1 is a position, so I have here my robot. x1, x2, and the robot is like this, with an input x1, x2, and the heading corresponds to x3. Now I have a desired heading. This desired heading could be, for instance, this one, as in called psi bar. So we can understand here that we have some kind of proportional control given in the exercise, and u equal to the sign of the error psi bar, the wanted heading, minus x3, the actual heading. So I consider this error and I take the sign because sometimes I can have some jump of the measurement of x3 that are more or less 2 pi, and I want that this is why I take the sign to avoid to filter the jumps of 2 pi. Okay, now here the input will correspond to psi bar. This is a control system. Now I have an automaton given here that will generate the psi bar, the wanted heading. So at the beginning, the wanted heading is I start with q equals 0, and the wanted heading is psi bar equals 0. So it means that I want my robot goes right, like this. So probably it will do something like this. It will go right, and I have a timer or a clock C, which starts at 0, and it is initialized at 0 each time that the state q jumps from 0 to 1 or 1 to 2 or 2 to 1. This is why q is a state vector which belongs to 0, 1, 2. This is why here in my Petri net, this automaton is a Petri net, I have 3 places because I have 3 values for q. Here are the transition, and my state jump from one place to another as soon as the condition is satisfied. So C is the clock. It starts at 0. Once I have obtained C equal to 5, I jump to Q equal 1. So I'm here. At time C equal to 5, so I jump to psi bar equal P divided by 2. This is why I will jump like this, turn, and probably go up. This corresponds to psi bar equal P divided by 2. And I will jump like this until a condition is satisfied. Once this condition is satisfied, maybe here, Then I will choose another heading which corresponds to 4, and probably I will turn like this, and this corresponds to psi bar equal to 4. And once I will be here, okay, I have a condition which satisfies is -2. So maybe I will go here, -2 maybe here, and then I will switch to q equals 0, so green, and I will do something like this, and etc. So since I have started here, probably I will turn here earlier than before, and I will go up, and so on. So what I want to show is that since here I have the line x1 equal -2, probably I have this one which corresponds to a parabola which can be something like this. Let's say this. This is a parabola. x1 plus x2 square equal 20. Then I have to show that I will converge to a limit cycle. From here, I return the values x1, x2 that are needed here for the conditions. The clock and q are both state variables that are inside the automaton. The closed loop system is this. And this is a closed loop system that will converge to a limit cycle. To prove this, by simulation, I will consider here this following Python program. I have here the main program with the initialization for x0, and I will also initialize the automaton with q equals 0, and the clock is also initialized to 0. I initialize my figure, and I will perform a loop by the function clock, which via an Euler formula will change the state variable x, q, and the clock also at each sampling time dt. So this is why here I put the dt, the sampling time, to 0.1. The state x, q, and c are parameters of the clock. Here I will add dt to the clock, and if one of the conditions is satisfied as given in the automaton, then I will increase the value of q. Of course, modulo 3, because when q equal to 2, if I add 1, I will switch to q equals 0. Each time q change its value, so each time one of the conditions is satisfied, the clock is initialized to 0. Here I have my dictionary, which tells me that psi bar of q is equal to, so for instance, if q equal to 1, it will give the value p divided by 2. So for instance, this one gives me psi bar of 1 equal to p divided by 2 as given in the automaton. I have also psi bar of 2 equal to 4. It is a dictionary in Python. I will also draw for different values of q a different color for the robot, so it is also a dictionary. At each sampling time, I will draw the tank with respect to the state variable. I will take the color given in this dictionary, which depends on the value of q. Here it's the size of the robot, just to see something on the picture. This is an Euler formula. So this is an Euler integration chain, where here this corresponds to u. And here it is a sawtooth function. I don't really need it, but it's just to due to this integration, then the angle will take will increase, and I want it to be always between minus p and plus p. This is why I will filter this angle by the sawtooth function, but I don't really need this function. I switch to Python. I run the program, and I see here that the car is moving and seems to converge to a limit cycle. The color of the car depends on the value of q. This is the limit cycle. I can understand that here I have q equal to 1 in my trajectory. So here it's for only one lap, and here I have many laps. And in the last picture, the car is represented by points to have a better view of the limit cycle. Oh, here the limit cycle, I start here, I move like this, and here I go here. So first here, then here, and after here, 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 and after I will converge to the limit cycle, which is shown here. Very quickly I converge to it. So this is all inside the limit cycle. Q equal 1 is in blue. Q equal 0, Q equal 1, and Q equal to 2 in green. I can understand that here it corresponds to x1 equal minus 2, and this probably corresponds to the parabola, because I switch from q equal to 1 to q equal to 2. So these are called surfaces. I will show later that are important to study the stability of the cycle. Question number 2. I take a surface in my state space of dimension n minus 1, where n is the dimension of my state space, which is given by an equation g of x equal to 0. So x is of dimension n and j of dimension 1. So we say that it is transverse to f if x belongs to the surface, implies that the trajectory is transverse to the surface. So I will explain this just later. So this surface is called the Poincaré section, and we'll see why it is important to understand the stability of the cycles. So we consider a point of the surface where the field is transverse, and we define the Poincaré map as a function which associates to a given state A the state P of A of the surface, such that the trajectory intersect S for the first time, after A, of course. And of course, I need the transverse condition to be satisfied in the right direction. So I will explain because there is a picture associated to this in the exercise, and I will show it now here. So I will come back and the picture is given here. This is a Poincaré surface in blue, and if I take a given initial condition, let's say for instance this point, then I will get a trajectory. So I consider a system like this, x dot equal f of x. I do not take into account q at the moment. So my trajectory will intersect j, the surface S, for instance at point A, and it will intersect several times when time is going to infinity. So the Poincaré surface is S, and I will consider the application which associate to A. So here it is transverse because I intersect the surface. I will consider the function which associate to A the first time the trajectory meet again the surface. So I can understand that here I will probably meet again, so this here, and probably meet again like this one. I will have here P of A, and so on. So I will have many applications, and if I have a look just on the surface, I can consider the application. So this is a surface, but represented in a Cartesian manner. So P, the Poincaré map, is the application which associate to A, P of A. And this one is probably some kind of convergence, we'll see, P of A, and maybe I will converge to one point if all the trajectory come back to the same point. Okay. So this is an illustration of what we call a Poincaré map. The question number 2. I consider the surface, which is given by x1 plus 2 equals 0. So remember that my system I consider is x dot 1 equal cosec 3, x dot 2 equal sine x3, and u equal sine of psi bar minus x3. So psi bar is assumed to be fixed and it will depend on q. So this one depends on q. So what happened is that here I have my state space x1, x2, x3, and I have some kind of plane corresponding here to x1 equal minus 2. And this plane is a surface, S. And the trajectory will cross the surface at some points. Okay. And it will cross several times. I have a condition which tells me that if I'm transverse, it means that the trajectory will not do something like this. Just touch the surface, intersect it, but come back from the same direction. So it is not transverse here. And I should understand if I am transverse to S or not. If I'm not transverse, I will have some difficulties to prove that I have a limit cycle. So the condition that is given is say that x, if x belongs to the surface, then it tells me that the derivative of j respect to x multiply by f at point x should be different of 0. So what does this mean? It means that if I have a surface like this one or like this one, let's say, so this is a surface. This surface has a gradient because it is defined by g of x equals 0. So here I have a gradient I call like this, for instance. And what is important is that the field, so this corresponds to the field, and this field tells me how the direction of the trajectories. So if f, the field, is orthogonal like this, it means that some trajectories may intersect but without without crossing the surface S. So it may be a problem. This is why I ask to have this condition. So I will check it. In my condition, in my situation, this corresponds to f of x. This corresponds to j. So I will compute the gradient of j. The gradient, so j of x is equal to x1 plus 2, and the gradient at point x is equal to the derivative of j with respect to x1, so it will correspond here to 1, 0, and 0. So if I multiply the two, I will obtain in my situation that this is equal to cos x3, because 1 multiplied by cos x3. As a consequence, I can conclude that the field, the vector field f, is transverse if the cosine of x3 different of 0. And I can understand this because in my situation I have here x1, x2. Here I have x1 equal minus 2. And if the car is like this or like this, okay, then I may have some trajectories like this. But if I am like this, for instance, so the cosine is different than 0, then I will cross the surface. Question number 3, I have to build a program, which will with Python here, which estimates the fixed point of the Poincaré map. So it satisfies this equation. So a remark is when I cross the trajectory, then Q switches from Q equal to 2 to Q equal to 0. I propose the following Python program, and the idea is to run a simulation and to isolate the sequence of all states x such that Q switches from 2 to 0. And I can take, since I'm quite stable, I will take a lot of iteration, but here it can be let's say 10 iteration. So this is the same program as before, clock, with the dt here, which is important, because I will ask here a very high accuracy. So we'll see later why, because to have a good approximation on some derivatives that will be computed just later. So the idea is the following. I will perform a simulation, and each time I have a Q that switch from 2 to 0, so this is the whole value for Q, which is memorized here. So each time that Q switch from 2 to 0, then I will return x, so it means that x is on the Poincaré section. So of course, each time I cross the Poincaré section, the clock has to be initialized to 0, and Q is also equal to 0. Okay, so let's say what happened here. This is my Poincaré surface, which corresponds to x1 equal -2. So recall that in the trajectory, here I will have q equal to 2, and then after I will have q equal to 0. And when I'm here, this condition will be satisfied. So I take a very good accuracy because it takes a long time to come back here, and if I want to have some accuracy here, I don't want all errors accumulate and give me a bad idea of where is the equilibrium point. So I take this initial condition, but another condition, initial condition, could be taken as well. I would have obtained the same result. Here I took only 10 iterations. I could have taken more, but since the cycle is quite stable, 10 is sufficient. And here I print the value just to have an idea if I'm far to the equilibrium point or not. I run the program and I obtain quickly that I converge to these values. I can understand that the value for x1 is -2, which corresponds to the Poincaré section. But I see that the values for x2 and x3 do not change when time is moving. This is why 10 steps was sufficient. The last question. I have to compute an estimate of the Jacobian matrix of this Poincaré section, of this Poincaré map, at point A bar, which corresponds to the equilibrium. And from this Jacobian matrix, I have to conclude about the stability. So recall that I have my Poincaré section like this, S, and from this, if I take x, this corresponds to P of x, but the Poincaré section is normally when I start from S and I come back here, so let's say x, and here it's P of x. Okay, so I will compute, I can see this as a discrete time function which tells me xk plus 1 equal P of x of k, P like Poincaré. So the Jacobian matrix of P. Jacobian matrix of P at point x is equal to the derivative of P1, because here I recall in my situation I am in x3. So the Poincaré function is a function which goes from S3 to R3, but if I can also have a restricted view of P, which tells me that P is going from S to S. So I restricted, so it's a Poincaré function restricted to S. So if I consider this function, then I will have here the Jacobian matrix, which corresponds to the derivative of P1 with respect to x1. Here P1 with respect to x2, P1 with respect to x3. Here P2 x1, P3 x1, and the last one, derivative of P3 with respect to x3. So we can understand that this derivative is not so easy to compute. I have to integrate a differential equation and then to deduce the derivative of the intersection. It's not so easy. This is why I will approximate by a finite difference method. So what does this mean? It means that I have here three vectors. And each of these vectors, for instance, corresponds to the derivative of p with respect to xj. So here, for instance, is the derivative of p with respect to x1. And this is approximately equal to p. So if I want to evaluate at point A, it will be p of a plus h aj minus p of a divided by h, where aj is equal to 0, 0, 1, 0, 0, where it is equal to 1 at jth position, is a jth canonic vector. And I have to evaluate this at equilibrium point bar here, where a bar satisfied p of a bar equal to a bar. Of course, h should be small. For instance, positive and small. For instance, I can take that h equal 0.01, something like this. I consider the Python program given here, where this is exactly what has been proposed before. This also. Okay, I compute here the fixed point. The fixed point has been computed in a three-dimensional space, x1, x2, x3. So here x1, x2, x3, where I can see that here it corresponds to the surface x1 equal minus 2. And so I can represent in this picture, this corresponds to x1, which is transverse, and here x2, x3, for example. Here it is a restricted view, where I have only x2 and x3. I am only interested what I have inside the Poincaré section with my discrete system. What I compute by a difference method is usually the Jacobian matrix, given here, is from R3 to R3, and I am only interested by this part, which corresponds to a projection on the x2, x3 space. So this corresponds to x2, x3, this one, is the second components p2, p3 of the Poincaré map. And then I will study the stability of this function, which tells me if I will converge to a bar here or not. So this is why here I take h equal to something small. I add 2x, which corresponds to the a bar to the fixed point. I will add something with respect to x2, and then with respect to x2, to x3, and I make the difference just to see the rate or the slope, or how the Poincaré function moves when I change x2 and x3. Then I compute, I will form this matrix. I will compute the eigenvalues here, and I will check the value of the eigenvalues to conclude about the stability. I run the program. It computes the fixed point here, the Jacobian matrix, only with respect to the coordinates x2, x3. Here are the eigenvalues, and both have a module which is smaller than 1. It means that the Poincaré map is stable. As a consequence, the limit cycle is also stable.